Hello everyone, today I'm going to talk about Aluminum-7075 produced by laser powder bed fusion and how to separate the main issue with this LPBF process alloy, hot cracking. Before getting to the heart of the matter, let me introduce a bit the subject. First of all, the aluminum that we are investigating is the 7075, which is mainly alloyed with zinc, magnesium, and copper that will form hardening precipitates. Aluminum alloy have an interesting strength to weight ratio, and among them, the 7000 series have a really high strength. And regarding the process that was used is the well-known LPBF process. It is one of the most widely used additive manufacturing technique for metals, and it allows the production of complex parts unable to be built by standard processing techniques. Like I just said, LPBF aluminum 7075 is highly susceptible to hot cracking. It is a phenomenon that occurs at the end of the solidification. The high cooling rate and the high thermal gradient of the LPBF process combined with the high solidification interval of the aluminum 7075 can explain this high susceptibility. As you can see on the optical micrograph, the hot cracking is mainly oriented parallel to the building direction. But how to avoid these cracks? Martins and co-workers have shown that one solution is to add zirconium to the initial powder. When a classical powder is used, the dendrites are growing in a columnar way, forming a microstructure composed of large elongated grains highly susceptible to hot cracking. When you add zirconium to the aluminum 7075 powder, the dendrites are forming preferentially on aluminum 3 zirconium submicrometers precipitates that are formed at the beginning of the solidification. It gives a microstructure that is composed of fine equiax grains that are highly resistant to hot cracking. In this presentation, I will analyze 4 different alloys. The first one is the classical aluminum 1775 without zirconium addition and will serve as a reference for the 3 other ones. The second and the third ones are aluminum 1775 with addition of zirconium hydrides by mechanical mixing. The difference between the two is that the second one has a lower zirconium content, while the third one has a high zirconium content. It will allow us to compare the effect of the zirconium content on the properties of the samples. And the zirconium hydride powder was sieved at 45 micron before being mechanically mixed in order to remove the biggest particles. For the fourth alloys, another way of adding the zirconium hydrides to the aluminum 75 powder is used. Indeed, zirconium hydrides is added thanks to AM4AM patented technology, which consists in the grafting of ceramic particles on the surface of aluminum powder through the means of an atmospheric cold plasma discharge. We are collaborating with this startup to fully characterize the impact of this innovative process on the final properties of the part since it is still under development. For more information about the plasma coating, you can refer to the patent that is mentioned on the slide there. For the coating, the zirconium hydride powder was not sieved. It has a lower zirconium content than the high zirconium content mix and could have more zirconium than the low content one. So you must keep that in mind for the comparison that will be made during the presentation. So now let's get to the heart of the matter, beginning by analyzing the properties of the powder. First of all, here is the granulometry analysis of aluminum 75 base powder. You can see that it has a classical size distribution with the mean diameters of 38 microns. Now let us analyze the zirconium hydride powder. In blue, the ZrH₂ powder, and in orange, the powder after being sieved. It has a mean the size around 13 microns for both condition, but the D90 of the powder after mixing is 6 microns lower than before, and this effect can be seen on this graph. Afterwards, we used low magnification SEM images to analyze the quantity of zirconium hydride particles that are present in the different powder. The aim of the zirconium addition is to have small zirconium particles grafted on the aluminum powder. The big particles that appears in white on the SEM pictures, obtained on the SEM pictures, are some zirconium hydrate particles. These large particles will be detrimental for the mechanical properties of the parts, and so we want to avoid them. Indeed, they will either form some large precipitate or stay unmelted and serve as preferential damaging sites. So we are able to quantify that amount of zirconium hydrate particles by using the image analysis software ImageA. We were able to count the number of zirconium hydrate particles and divide it by the surface occupied by the aluminum 7075, and thanks to that, obtaining density of zirconium hydrate aggregates for the three different alloys containing zirconium based on a series of SEM images like the one you have just seen. We are also computing the average size of these particles, and you can see that for the three different alloys, it is roughly the same, around 10 microns, and it's corresponding to the size of the zirconium hydrates powder. And what is really interesting there is that the zirconium coated powder exhibits respectively 3 and 5 times less particles than the low content mix and the high content mix powders. It shows that the plasma coating successfully limits the number of these unwanted particles, even though the zirconium hydrate powder used was not sieved before the plasma coating. Now that we have talked about the unwanted particles, let us talk about the wanted ones. That is to say, the zirconium hydrate particles coated on the aluminum 7075 powder that can be seen in white on the high magnification SEM images. Once again, we will quantify the difference for the three different powders by image analysis. It is exactly the same type of image analysis than the previous one, but this time for the small zirconium hydrate particles that are grafted on the aluminum 7075 powder. If we compute the size of these small particles, we can see that it is below 1 micron for the three different powder mix. What is really interesting to notice is that the plasma-coated powder exhibits much more zirconium particles on its surface than the low content mix and the high content mix. So once again, the quality of the powder is better for the plasma coated one, even though the zirconium hydrate's initial powder was not sieved. Now that the powder has been thoroughly analyzed, let's look at the LPBF optimization process. We will look at the relative density obtained by the Archimedes methods for half cubes of 10 millimeter size, processed with a fixed etching space of 100 microns and a fixed layer thickness of 30 microns. We have tested a lot of different combinations of laser power and scanning speed, and we found that the low laser power of 164 watts gave the best density results. So we'll only analyze this low power value for this presentation, and we can see that there is an optimum in the density just above 98% for the high content zirconium mix and the plasma coated powder, while it is just below 98% for the 7075 and for the low zirconium content powder mix. The relatively low relative density is due to the lot of evaporation of zinc and magnesium during the LPBF process, and also due to the hydrogen released by the zirconium hydrates particles during the process. So during the rest of the presentation, we will only analyze samples with these optimized parameters, which are as a power of 164 watts and a scanning speed of 200 millimeters per second. So now let us look at the outcracking behavior of these four alloys. Firstly, the aluminum 7075 that you have already saw at the beginning of the presentation exhibit a lot of outcracks. We can link that with the elongated grains exhibited in the optical pictures of the etched samples. By using the linear intercept method, it was possible to approximate the mean grain size around 40 micrometers. For the low zirconium content mix, the zirconium managed to reduce the amount of hot cracks. However, it does not manage to suppress completely the hot cracking. But let us look at its microstructure to understand this phenomenon. By looking at the optical micrograph, we can see some big columnar grains that remains and that crosses several melpools. And you can also see the grain refinement effect of the zirconium at the melpool boundaries. So we can distinguish a bimodal grain structure composed of fine grains located at the melpool boundaries and of coarse grains inside the melpools. If we quantify the size of these grains, we can approximate at 9 microns the coarse ones and at 1.1 microns the fine ones. Now, if we look at the high content zirconium alloy, we can see that the hot crux successfully disappeared. It can be explained by its microstructure when no more grains crosses the melpool boundaries. Moreover, the fine grains regions occupy a larger portion of the microstructure, sometimes occupying entire melpools. Even the coarse region have grains smaller than for the low zirconium content alloys. However, the fine ones are about the same size, so it can be concluded that the zirconium content will influence the relative portion of microstructure occupied by small equiax grains. If not enough zirconium is added to the aluminum 7075, hot cracking cannot be entirely avoided for this processing parameter. For the coated powder now, there is also a total suppression of hot cracking. The microstructure is quite similar to the high content one with the same bimodal structure and grain size, but with a bit less relative portion of the microstructure occupied by the fine equiax grain. It is a really encouraging result because it seems that the suppression of hot cracking can be obtained with less zirconium than for the high content zirconium powder mix. However, we cannot compare the coating directly with the low content powder mix since the coating composition still need to be precisely determined. Now that the optical microstructure have been analyzed, let's look at the SEM pictures to describe the microstructure more closely. First of all, we can see that the microstructure of the aluminum 7075 and of the mix with low zirconium content are quite alike. A finer microstructure that delimits the melpool boundaries, and some continuous networks of precipitates that delimits grains inside the melpools. We can also notice a small equiax grains region for the low content zirconium mix. These fine equiax regions are more present for the two others alloys, especially for the high content zirconium mix on these pictures. For all alloys, there is also some globular precipitates spread evenly inside the coarser grains. Now, if we zoom in more, we can observe a few other things. First of all, we can see more clearly the precipitate networks that delimitates the grain boundaries for the aluminum 7075 and the globular precipitate inside them. And the second feature to observe is the aluminum 3 zirconium precipitates that are preferentially located inside the grains and that have a recognizable cuboid shape. And you can see a zoom view of two of them just there. Now that the has-built microstructure has been analyzed, let's see how heat treatment will affect the microstructure. The classical T6 heat treatment used for the aluminum 7075 will be analyzed. It is thanks to this heat treatment that the 7075 obtained its higher strength by controlling its precipitation. This treatment is composed of two phases: the solution heat treatment, which is 1 hour at 470 degrees to solutionalize the uncontrolled precipitates of the has-built microstructure, and the aging heat treatment, which consists in 24 hours at 120 degrees, and that will control the growth of the precipitates to obtain the desirable hardening eta prime precipitates. On this micrograph, for each alloy, the network of precipitates delimiting the grains was globularized by the solution heat treatment. Moreover, the globular small precipitates inside the grains are less visible. We can also see the grain boundaries as highlighted on the pictures. The proportion of second phase is more important for the plasma-coated and the high-content zirconium mix than for the two others, since there were higher density of grain boundaries for these two alloys. All these precipitates still need to be identified precisely with TEM analysis. Now let's look at the microstructure after the complete T6 heat treatment. We can see that there is not much change compared to the solution heat treatment. So let's now link this microstructure with some micro hardness results. This final graph compares the micro hardness of the 4 alloys in the as-built condition with the hardness after the 2 heat treatment I've just introduced. First of all, we can notice that for the as-built condition, there is not much difference in the hardness for the 4 alloys. The second thing to notice is that there is not much difference between the solution heat treatment and the complete T6 heat treatment. It is a bit strange because normally it's the aging step that brings the high strength of the aluminum 7075. But since there was not much difference in the microstructure, it supports our observations. We reach a maximum of 181 vickers for the aluminum 7075 with high content zirconium hydrides, but there is still room for improvement for that value since the aging treatment seems to have no effect at all. So we are currently still optimizing the heat treatment. Finally, we can see that the aluminum 7075 and the low zirconium content powder mix have a low value of hardness, which is not quite surprising because the microstructure was coarser and there remains some crack inside the microstructure. And finally, the coating, the plasma coated powder exhibits a lower hardness than the high content ones, probably due to the fact that there were more fine aqueous grains for the high content zirconium powder. The last thing to mention is that these values of micro hardness are obtained for samples that have lost a lot of zinc and magnesium during the process, so are supposed to have less alloying elements to form hardening precipitates. So thank you for listening to this presentation, and that I hope you have enjoyed. And I leave you with the summary table of what I said about the 4 alloys that were analyzed. See you during the conference.